All right, so this is good. We're moving at a good clip here. Tomorrow you'll get your first assignment package for this course, which will cover up to lesson 1.5. On Thursday, we'll start off with a little quiz, just so you know. So just to sort of plan your week ahead. The assignment package you'll have until Monday to do. The quiz, obviously, you'll do on the day of. When your assignment pack comes, your assignment packages are always individualized, which means that I go to all the trouble of giving everybody different and unique questions, which also means that when I inevitably, and I always say this, and then inevitably somebody copies off someone else, and I'm like, you cheated. And they're like, no, I didn't. I'm like, I think you did. And they're like, I didn't, I swear. And I'm like, you have all the exact right answers to Max's assignment, and none of them are right for your assignment. You don't think that's oddly coincidental? Do you see what I'm saying? And then people will still just look you in the eye and be like, I did not cheat. And I'm like, I'm going to go ahead and say you did. But, you know?
What if they did it and they just... It's a possibility.
I mean, I don't know that meaningfully it is a possibility. But anyway. You do learn in teaching that people will very convincingly stare you in the eye and just lie to you repeatedly, which is something I don't know that I was aware of before becoming a teacher. And then I became a parent to teenagers, and then that confirms for you the ability to people to just stare right at your eyes and very convincingly and often very angrily lie to you. Anyway, that's neither here nor there. Yes. Monday's off, yeah, and Friday's off. Oh, sorry, it'll be due Tuesday. That's right. I'm not gonna be like, and everybody's late. 5%. I mean, that would be fun, but I won't do it. I promise. I mean, fun for me, not for you. Yeah, fun for me. Which is, to be clear, all I care about. But anyway. All right. This year, as we go through and re-teach and relearn chemistry that you probably already know, right? The idea of you guys already knew the difference between ionic and covalent compounds and things like that, right? Hopefully we're gaining a little bit of depth of understanding of these things as we go. Maybe not, I don't know. But here, for example, when we talk about ionic bonds, I want to talk about why we get ionic bonds, as opposed to covalent bonds, or as opposed to nothing happening at all. In other words, you know that if magnesium bumps into oxygen, they're going to form a compound, and that compound is going to be ionic. Because in grade 9 and grade 10, you learned that a metal and a non-metal form an ionic bond, right? And one gives electrons and one takes. Okay, why? Why? Why does that happen, as opposed to them bumping into each other and nothing happens, right? Or as opposed to them bumping into each other and they form a covalent compound, or as opposed to they bump into each other, form an ionic compound, but magnesium gets electrons and oxygen gives them up. Why? Sorry? Sure, the universe isn't nice. The universe is a cruel place governed by uncaring laws, Sam Brady. And the faster we learn that, the better off we'll all be. Yes? Yeah, right? The answer is that chemistry is in the end just applied physics. And physics tells us that what always happens is the easiest thing. And by easiest, we mean lowest energy. Just the thing that requires the least work from the universe is what happens. Does that make sense? We call these low energy states. But basically, water flows downhill, it doesn't flow uphill. Because it takes less energy for water to fall down the hill than it does for it to fall up the hill, and so it just doesn't fall up the hill. And I promise, you've never seen a hill with water on it and watched the water flow up to the top of the hill, right? You've never had water spilled on, and if you think about it, it's weird, but right? You've never had water spilled on a table, come up with a cup, and the water just flows into the cup, right? You've never seen that happen. On the other hand, if you turn the cup upside down, the water will inevitably fall onto the table, right? Which to you seems obvious because you've had a whole lifetime of experiencing that to know that that's true, right? But on the other hand, why not, right? Why doesn't water flow into the cup? And the answer is that that's a high energy state, and the universe doesn't move to high energy states. The universe moves to low energy states. The natural thing happens. And that's where electronegativity comes in. Electronegativity is just a measure of how much an electron has an affinity, or an atom rather, has an affinity for electrons. It's a measure of how much an atom tends to gain an electron. Or another way of saying is it's a measure of where it's easiest for electrons to go. Does that make sense? So when we say that fluorine is electronegative, really what we mean is that it is really easy for electrons to go to fluorine and to be in a fluorine atom with an extra electron, much more so than it is for another electron to go to francium. That's very hard for an electron to do. And the reason it's easy to get to fluorine is that fluorine only has 2 shells, so it's a relatively small atom, and it's got, even though it only has 2 shells, 9 protons hanging out in its nucleus, so it's got a big old positive charge, and the outer shell is close to that big positive charge. And as a result, it's very easy for electrons to get attracted there and stay there. Does that make sense? So, electronegativity is a measure of an atom's pull on new electrons. This should have an apostrophe in it because we all understand how apostrophes work, which is to show the possessive. So why I didn't put it there is an indication of my failure as an educator. The higher the electronegativity, the higher the tendency of that atom to gain electrons. So as a rule of thumb, metals, which is the right side of the periodic table, have high electronegativity. I'm sorry, I said metals, but what should I have said? Yeah, whoops. This is why I normally have my cheat sheet in front of me, so I don't accidentally misspeak. And metals, which are which side of the periodic table? The left side of the periodic table, typically have low electronegativity. Right? And so, as a result, nonmetals, under certain conditions, bless you indeed. Alexander, my friend, you guys are on note today. You already have the note, and it's on the OneNote. So as a result, nonmetals, under certain conditions, can take electrons from metals. But not, typically speaking, the reverse. So if conditions are right, chlorine will be able to take an electron from titanium, but it would be extremely odd circumstances if titanium was able to take an electron from chlorine. And again, that's a measure of electronegativity. That's a measure of the ease of which. And again, the reason for that all has to do with the arrangement of nucleus and orbitals, right? We basically said those small atoms that have, electrons close to the nucleus not only hold on to their electrons, but will grab on to other electrons with relative ease. And on the other hand, these big, massive elements on the bottom left of the periodic table, where the electrons are very far from the nuclei, do not have much pull on their own electrons or on other electrons. So that's one piece of it. And then the other piece is stability. I want you guys to come on a little field trip with me. Field trip to the prep room. So that is what I want to stress, which is that when you talk about things spinning in orbits that have mass, balance is really important. And when we talk about things being stable or unbalanced, we're not talking about that in some like hypothetical thing, or we're not talking about stability the way we talk about like mental stability. We're talking about a physical process here. Does that make sense? Where like you have electrons that are light, but they have mass. Relative to that steel and aluminum centrifuge, which weighs about 30 pounds, those little epipipettes probably weigh, I don't know, a couple of 10 grams, right? Very, very small weight relative to the weight of that thing. But two of them, misbalanced and spinning, make that thing start going out of control. Does that make sense? We saw that, right? And if I had let it run, I never let it get to full speed, it would shake itself apart. Like they're very clear that if you misbalance a load, in a centrifuge, you can break it, right? You'll destroy it. So like I remember in lab, like a washing machine, right? There's that scene in The Simpsons where they have like the washing machine races in the bar. But I used to have a washing machine like that where every time you ran it, like you'd come into the room later and it was on the other side of the room, like and had like unplugged itself because it just would not stay balanced anymore. But I couldn't afford to replace it. So this is completely true. So I built like doorstop style wood wedges that I just drove under it in its spot and just like it would shake and shake and shake. Anyway, point being, that washing machine didn't last too long, right? Because things need to be balanced. So I think that helps to understand that when we say that an orbital has to be full to be balanced, it's not like some hypothetical thing. It is literally, you're talking about masses revolving at extremely high velocities. And if those aren't balanced out, the thing will fly apart. Yeah. Yeah, So, great question. The answer is everything we're talking about here is at the electron level. So we're talking about chemistry, and chemistry happens with electrons, but the exact same thing happens in nuclei. We think of nuclei as being this solid thing, but actually the nucleus itself, the protons and the neutrons, are made up of smaller particles called quarks and gluons and all these other things, and they are also spinning and moving. And so the nucleus itself is only stable under certain conditions. We're not going to talk about that because this is a chemistry course, and that's a topic called nuclear physics because it's about the nucleus, but it's the same idea, absolutely. And that's why when we talk about isotopes, you can have carbon with 6 neutrons, and that works. You can have carbon with 8 neutrons, and that works. But there is no stable carbon with 10 neutrons because the nucleus itself would fly apart, and in fact does. So a lot of the isotopes that we find for these things, have you guys heard of like the Large Hadron Collider and CERN and these things, like where it's literally a particle accelerator, so a big thing designed to speed particles up and hit them together, and it's the size of a city. Like literally it's built in a big tunnel around Geneva, Switzerland, and they are bashing particles together at just near the speed of light. And we can create new nuclei that don't exist before, but if the nucleus isn't balanced, it will decompose. It will fall apart. It will what we call decay in a matter of nanoseconds sometimes. Like sometimes these things exist just for fleeting periods of time. And that's the answer to your question, which wasn't a dumb question at all. It's a great question. But for the purpose of this course, we're going to deal with electrons and orbitals, and we're going to assume that we have stable nuclei. Does that make sense? That was a good question. So electron orbitals that are not full are unstable. And that can range from being completely unstable to simply not as stable as if it were full. And it really doesn't matter. Because remember we said water always falls downhill? Right? Even if the top of the hill is completely untenable and the middle of the hill is sort of untenable, it's still always going to go all the way to the bottom. It's going to find its most stable spot. Does that make sense? Likewise, the most stable way to be as an atom is to have a full shell of electrons. Does that make sense? So, electron orbitals that are not full are unstable. atoms will gain or lose electrons according to their electronegativity to form empty or full valence shells. Obviously, an empty shell is stable because if the shell is empty, it's not there anymore, right? Like the shell isn't. It's important to remember that an electron orbital isn't like a thing that electrons fit into. It's not like a. Oh my God! It's not like this thing. Wow, talking about unstable. Sounds like it's had better days. Jeez, I'd be really upset if I hadn't just stolen this from the advanced program one summer. Anyway, we don't talk about that. Sorry? I guess I did, yeah. I just took it. I also took a couple little couches they had, and they came and took those back, but they didn't come take the lectern back, so I thought that was a victory. The cops, I think they have better things to worry about than me having stolen a lectern 11 years ago. But maybe I'm wrong. Maybe they'll come get it. Anyway, to form empty or full valence shells. And you can tell just looking at the periodic table, we're about to look at down below, but if you look right here, how many electrons would sulfur have to gain to have a full shell? 2. What about silicon? 1, 2, 3, 4. Silicon could also lose potentially 1, 2, 3, 4. Silicon sometimes will lose electrons. Mostly it will gain them. Mostly it forms covalent compounds. What about carbon? It could potentially gain 4. It could actually, under really rare conditions, lose 4, right? Yeah.
Sulfur needs 3 electrons, right? Oh, never mind. It just clicked in my head.
No problem. Yeah, sulfur, how many does it need? 2, right? On the other hand, if we go over to magnesium, is it going to gain electrons? How many would it have to gain? 1, 2, 3, 4, 5, 6, I think, right? But A, that's a lot. B, magnesium is not highly electronegative, so it's not going to gain 6 electrons, because to do so, it would have to be highly electronegative, which it isn't. So it's not going to gain electrons, it's going to lose electrons. 2 things that are highly electronegative. How many does it have to lose before it empties its shell out? 2. What about potassium? No. Okay, now, we are going to say one thing. Oh my. Note, the middle of the periodic table, whole different ball game. And the reason it's a whole different ball game is just that these orbitals are really big. And in a really big orbital, there's some ways to be stable without being full or empty. Does that make sense? You saw it back on that thing. I don't have to, if I put a little thing in every single slot in that thing, it will run steadily for sure. But there's also different patterns you're allowed to use. You can have them be opposite from each other. You can do 4. You can do 6. Does that make sense? There's some combinations in there that work as long as they're symmetrical. Does that make sense? So a note, the middle of the periodic table don't typically go for full or empty shells. But rather stable partial shells. And they're able to do that because their shells are big. Does that make sense? Now, having said that, are they going to gain or lose? Why are they going to lose if there's different stable conformations? And probably there's somewhere a couple extra electrons would also be stable. Yeah, which means that they have a very low electronegativity. Good. That was a great answer. Does that make sense? But just know, so you'll probably notice that in grade 9 and grade 10, we mostly ignore the center of the periodic table, right? We just kind of pretend it's not there when we're making questions. This year we'll get into it, but it's much harder to make predictions about because it's just got these big orbitals that can be worked with in different ways. You would have probably talked about a few of the multivalent metals last year, like how some, is that what you're going to say? Yeah. Yeah, we are, for sure. Not today, but we are. So iron, for example, has 2 ways it can become stable. It can lose 2 electrons and be stable, or it can lose 3 electrons and be stable. And actually, it's also stable having lost no electrons, right? Its current arrangement, it has a big enough shell that it can be quite stable. Iron, a pretty stable thing. But you put it around something that's highly electronegative, and it's still going to give away its electrons, right? Because that's what electrons do. They go to the easiest place. Water falls down a hill. Electrons go from atoms that have low electronegativities to atoms that have high electronegativities. It's just what they do. So, generally speaking, you shouldn't need a chart like this. You can see it right away, right? Why does aluminum take a +3 charge? Well, it takes a +3 charge because it has how many electrons in its outer shell? 1, 2, 3. And to become stable, the easiest route to that is just to lose all 3 of those. And in so doing, it takes a charge. A positive charge. I really meant to write on that, but it really... That's right. Yeah, electrons have a negative charge. So if you give away negative things, you become positive. And if you get negative things, you become more negative. So the metals are always going to take what kind of charge? Positive charges. The non-metals are always going to take negative charges. And again, this little chart gives them to you, but you shouldn't need this chart to give them to you for anything but the weird middle. Zinc, on the other hand, would you be able to predict, just looking at the periodic table, that it would give up 2 electrons? I wouldn't, right? Like, I don't know why that would be more stable. Likewise, would you be able to predict that silver gives up 1? I wouldn't. So when we get to the middle of the periodic table, things are more complicated. Does that make sense? And you know, we didn't figure it out by looking at the periodic table and predicting. We figured it out by just doing experiments. You take silver, you react it with stuff, and you figure out how many electrons it lost. Does that make sense? Okay, so let's just remind ourselves how an ionic bond forms. And we're going to do that by looking at Lewis structures. And we'll start with that classic example, the one you always see, sodium chloride. So we're going to react sodium, which has what formula? Na. How many electrons in sodium's outer shell? Yeah, it only has 1 electron. Good. And we're going to react it with chlorine. And how many electrons in chlorine's outer shell? Yeah, chlorine has 7. And I'm going to color code these so we can kind of keep track of where they come from. Sometimes you'll see in diagrams they will mark, one of them with X's and one with dots. Whatever. Just helps to kind of keep track. And which one of these has a high electronegativity and which has a low electronegativity? Yeah. Chlorine has high electronegativity. Sodium has low electronegativity, which means the electrons are going to flow from low to high. That's the way it works. So sodium will donate an electron to chlorine. When that happens, what does sodium look like now? Well, its valence shell now is empty. In a Lewis structure, whenever something has a charge, how do we indicate that? Square brackets. Very good. And what is the charge in this case? +1. Yeah, you guys had good grade 10 teachers. That's great. I love it. What does chlorine look like now? Good. For a total of how many? Good. And I want to be clear, we're only coloring these to keep track of them. It's not like sodium has some kind of different type of electron than chlorine. So an electron is an electron. Now, will it have a charge? How do I indicate that? Square brackets. And we write the charge. In this case, it is -1. And these are held together by what force? By the force of attraction between opposite charges. You've heard the expression opposites attract? Yeah. But something that is positively charged will always be attracted to something that is negatively charged. And so this, sodium has positive charge, chlorine has negative charge, they'll be attached to one another. And this could keep growing as a crystal. If we had another sodium and another chlorine show up, that sodium could give its electron away to that chlorine, and that sodium would want to find its way next to this chlorine, and that chlorine wouldn't want to be next to this chlorine, it would want to be next to a sodium. Does that make sense? And they just keep growing out. And as they keep growing up, they form a big crystal. This is an ionic compound, so it's just going to form a crystal, where for every one sodium, you get one chlorine, and they just grow out and out and out. It's a big dumb rock. That's what ionic compounds form. Big, dumb rocks, minerals, right? And beautiful minerals. You can go and see, go to a geology museum. You'll see some of the most stunning, we went to the Museum of Natural History in Manhattan a few years ago, and they have these geodes that are just stunning, like just taller than I am, bigger around, just incredible colors and beautiful things, but they're just big dumb rocks. They're just atoms growing in the same pattern over and over and over again. We would call this, so sodium plus chlorine gives us sodium chloride. Good. Why not sodium monochloride? Sorry? We don't use prefixes. Why don't we use prefixes? Don't I need to know that it's 1 and 1? Why do I need...
No, it's 1 and 1 because it doesn't have a charge next to it.
Okay.
So you cancel them out if it's 1 and 1.
Sure. But what if it had been sodium oxide, in which case there'd be 2 sodiums. Don't write this. In which case it would be this. Would that be disodium oxide? No. Why not? Because when it comes to ionic compounds, there's only ever one way to put them together, because they're big dumb rocks. So we don't need to tell you how many, because you can figure it out yourself. With covalent compounds, you can put them together any way you want. So when I say you put carbon and hydrogen together, you say, okay, which one of the literally infinite ways? Because there's an infinite number of ways to put carbon and hydrogen together. I guess it's not infinite in that there's not an infinite number of atoms in the universe, but that's really the only boundary, right? Like you can put them together any way you want. So the name needs to tell us how they're put together. In ionic compounds, there's only one way to put sodium and chlorine together. Sodium's going to give its electron to chlorine. They're going to stick together. They're going to form a crystal of 1 sodium for every 1 chlorine. And the fact that sodium and oxygen has a different formula, it doesn't matter. The name doesn't need to tell you that, because you can figure that out. Does that make sense? Okay. We would refer to these as atoms. These are atoms. What would we call these once they have a charge? They're not atoms anymore. They are ions. Very good. Any charged particle, and it doesn't have to just be an atom. A charged molecule is still called an ion. An ion is a charged particle. And the naming convention, we just name the cation, then the anion, with the ending changed to "ide." What do we mean by cation and anion? Did you see those terms last year? Great. Which one's which? Good. We'd call this the cation, and that's so called because it's positive, and we'd call this one the anion, and it's so called because it is negative. Good. And by the way, the naming convention also, it's just like the periodic table. The name starts with the thing on the left, then the thing on the right comes, and we change the name ending to "ide." Good. Okay. Let's try another example using magnesium and fluorine. So magnesium has what symbol? Mg. And how many electrons in its outer shell? 2. And fluorine has what symbol? F. And how many electrons in its outer shell? Okay, take a minute and draw this. Show me what you get. I will return.
Would this happening make it possible? God, can you bring it over here? I don't want to. Sorry. Thanks. Does everyone have their lab notebooks in? I'm gonna take that as a yes. No, I'm not really thinking of you. I'm just like losing my mind. I don't know if that's how I feel. I don't know.
Very long.
Maybe another person can use last time.
What? You have a library. Why are you going to? What else is libraries?
Alright, you tell me why.
Because it needs to be a person that's certified. I'm sure there's just one that's certified.
I mean, to clean it, and you can learn how to clean it, but sometimes I forget to put it in cleaning mode, so then it gets turned into cleaning mode like 8 a.m. and it's pretty so. Like, because cleaning mode is supposed to happen at 3, but sometimes 3 will turn off. But to take it apart, you should technically have combinations. I don't, but I learned how to do it. Well, no, they're also kind of trying to make me work on 5 hours a week and work over part-time hours, and also stay more than 2 hours. And they all usually apply when they're telling them to
Look at the periodic table. So visually, where's cesium? Which row? 1, 2, 3, 4, 5, 6. So you're right, it's after xenon. And then what's that? What? Those first two rows are always what? What orbitals do those represent? Right? The first two columns represent the s orbitals. The last 6 represent the p orbitals. Then the middle represents the d. And then the lanthanides and the actinides represent the f. So cesium, what orbital are we in after xenon? Xenon, and then we have the 1, 2, 3, 4, 5, 6, so 6s. Does that make sense? All right, talk to me. How's this work? Go. Hi, welcome. Note is somewhere. Note is on my desk, maybe? Yeah, on my desk. Yeah, talk to me. Ah, good, because magnesium's going to give its electron to fluorine, right? And that fluorine now has a full valence, right? So it's going to be here, and it's going to have 1, 2, 3, 4, 5, 6, 7 of its original electrons. The 8th that's received from magnesium. Because it gained an electron, what charge is it going to take? But magnesium isn't stable because it still has an electron left, and it can't give it to that fluorine because that fluorine now is stable. And we know that things are stable don't take electrons, right? The noble gases don't take electrons. So what we need is just a second fluorine, right? And that second fluorine has 1, 2, 3, 4, 5, 6, 7 electrons, and magnesium will donate its electron to it. What would most likely be here next to this fluorine? The magnesium. What's its outer shell look like now? It's empty, and its charge? +2. And then down here we would have the other fluorine. And what charge does it have? Great. Does this work? Yeah. Oh, great. So the answer is, by the way, you could have a situation where magnesium gives one of its electrons to a fluorine, and if a chlorine also happened to be around, it could give the second one to a chlorine, and it could be here. And you could now have MgFCl. That's fine. So the reason why you can do this is because atoms are so tiny, you're never dealing with one. If you take a sample of magnesium, you have, trillions upon trillions upon trillions of atoms. And if you take even a small sample of chlorine, you have trillions upon trillions upon trillions of atoms. When you bounce them together, there's just lots of atoms around. Does that make sense? So the reason you can do it is because in the real world, you're never dealing with one atom and one atom. You're dealing with trillions and trillions. So any one you look at can interact with as many fluorines as it needs to because there's just limitless around. And chemistry is always based on the assumption that there's lots of everything involved. If you get down to the individual atomic level, and if you actually put one magnesium near one fluorine, they wouldn't be able to stably react. But that's not how reactions are done in the real world. Did that answer your question? You're just saying that to shut me up?
Well,
a little bit?
It's also just that I know a lot of chemistry. It's just like, you can do this because you can do it.
Yeah.
Unless like this happens, then you can't do it. So
Yeah.
it's kind of like,
Yeah, one thing to keep in mind is that we're teaching you in sort of ideal conditions, right? Where we're assuming that we have just these two things around. Bless you. But yeah, the answer to why can you just add another one? Because if you're reacting with magnesium and fluorine, you have lots of both, is the short answer. And the formula for this would be MgF2, and we would call that magnesium, not magnesium difluoride. Why not? Okay, but why? Why don't we name ionic compounds with prefixes? Big dumb rock. It can only come together one way. If you put magnesium with fluorine, this is the only combination that works, right? Again, if you put magnesium, fluorine, and chlorine together, you could get a different combination. Or if you put magnesium, fluorine, and oxygen together, you could get different combinations. But if the only thing you're putting together is magnesium and fluorine, this is the combination that works. So when we make magnesium fluoride, we don't need to be specific with the name because this is the only possible combination. Make sense? Cool. All right, now, do we want to draw this every time? Okay. Now listen, some teachers teach like the crisscross rule, where they show you to like write the numbers down and then just cross them down and then reduce to lowest terms. I think that is fine. It's certainly a perfectly reasonable method. It's how I was taught. But I don't think it promotes understanding what's going on. And like you asked, a lot of times our chemistry ends up being like, do it this way. Why? Because that's what we told you to do. And I don't like that. I prefer things that promote understanding. So I'm going to show you how I work out formulas. And the nice thing is, this will work for what we're doing today, which is simple stuff off the periodic table, binary compounds. But it's going to work just as well when we get to radicals. It'll work just as well when we get to multivalent metals. And it'll work just as well going on when we do like grade 12 chemistry and stuff, because it's not a trick. It actually just promotes you understanding what's going on. Which is like the advantage of drawing it is it helps you have a good understanding of what's going on. Why do we have 2 fluorines here? Well, we have 2 fluorines here because when the first one took an electron from magnesium, magnesium's shell wasn't empty yet. Does that make sense? So what I would do is instead of drawing that, the other thing I could do is I could say, well, let's look at magnesium and let's look at fluorine. And let's just say, what charge do they tend to take? Magnesium has how many electrons to give away? 2. So it can give away 2 electrons every magnesium. So if I had 1 magnesium, how many electrons would they be able to give away? 2. If I had 2 magnesiums altogether, how many electrons could I give away? 4. What if I had 3? How many could I give away? Okay. On the other hand, fluorine, how many electrons does it take? Just 1, right? It can only take 1 before it has a full shell, which means we say it takes 1 electron or it takes a charge of -1, which means a single fluorine could take 1 electron. 2 fluorines could take 2 electrons. 3 fluorines could take 3 electrons. And then the combination that works is where these balance each other out. Does that make sense? So, how many fluorines have to meet up with how many magnesiums for it to work? Well, 1 magnesium gives 2 electrons, but that requires how many fluorines? 2 of them. And so I would say 1 Mg is going to end up with 2 fluorines. I mean, I wouldn't actually draw over it like that with a pen, but I draw this little table. And at first you may say that seems more confusing. My belief from having taught this now for 13 years is if you stick with it and start doing this as a bit of habit, you'll not only get the right answers, but you're not doing some little math trick. You're not flipping the 2 numbers over. We're kind of talking our way through why it works. Does that make sense? And again, if that seems confusing at first, sure, it's confusing at first. Stick with it. And so the formula for this would be 1 magnesium with 2 fluorines. And then as a rule, do we write the number 1 if that's all we have of something in a formula? No, and so it would just be MgF2. And that is a little bit of drawing, but it's a lot less drawing than all of this jazz, right? I'm not drawing dots. Does that feel okay? Let's try another one. Calcium phosphide. Okay? So before we do anything, what compounds are we talking about? Calcium is Ca. And phosphide tells us that we're talking about phosphorus, which is P. Okay? So we're talking calcium and we're talking phosphorus. And as we talk about calcium and phosphorus, I'm just going to do the same thing. 3 will almost always get you there. You can add more columns if you need. How much does every calcium give away? How many electrons? Yeah. And how do we know that? We come and look. Calcium in the second column, meaning it has 2 electrons in its outer shell. So to have an empty shell, it would have to lose both of them. So it's going to lose 2 electrons, which in terms of charge, we indicate how? +2. We say that this can lose 2 electrons, which means a single calcium would be able to give away how many electrons? But 2 of them would be able to give away, and 3 of them would be able to give away 6. Okay. What about phosphorus? Phosphorus receives how many electrons? It only has 1, 2, 3, 4, 5 in its outer shell. What's a full outer shell? 8. So it has to get how many more? 3. How do I indicate that charge-wise? -3. So a single phosphorus will gain how many electrons? 2 of them would gain how many? 3 of them would gain how many? I could keep going, but do I have a match here? Yeah, what's the match? The match is that if we have 2 phosphoruses, that's going to give away how many electrons? And on the other hand, how many calciums does it take to provide 6? Yeah, if we have 3 calciums, it can provide 6. Does that make sense? So that's where they match up. So what's the formula of this thing then? Yeah, it takes 3 calciums, so Ca3, and then how many phosphoruses? 2. Ca3P2 is the formula for calcium phosphide. Good. That was given in the question, but that's okay. It never hurts to rewrite it. Does that kind of make sense as a way of doing it? Again, it may feel like more work if what you were used to being taught was write the charge up here, write the charge up here, and now flip them down, and now it's Ca3P2. My problem with that is, inevitably I start getting this. Ca -3, P + 2, right? And it's like, well, what's that mean? And people don't know what it means. They're just writing it. Whereas this is a bit more work, it's a bit more drawing, but I think it really does phosphor, like, I said phosphor because I was looking at phosphorus. I think it really fosters, with a t sound, understanding what's going on. Yeah.
So from here we know that calcium would be in the brackets +3 and then.
Nope, calcium, each calcium, if we were to draw it, calcium has 2 electrons, right? So once it's given them away, if we were going to draw it, what would the calcium look like? It would have what charge? We already said. +2. What this means is how many of these would we have? We'd have 3 of them. And each phosphorus is going to take in 3 extra electrons, right? It's going to take 1, 2, 3 in, so that when we're done, it's going to have what charge? What charge does the phosphorus have? -3, but how many of them are we going to have? 2 times them. And you'll know it works because the charges have to balance. If something is receiving 6 electrons, then something had to give away 6 electrons. Does that make sense? We call that the law of charge balance. The law of charge balance, I think this is more confusing than helpful if you come look at this note after the fact. So I'm going to erase it. So each calcium loses 2 electrons. We need 3 of them so that it gives away 6 electrons, so that each phosphorus that gains 3 electrons can do that, and that's going to require 2 of them to get those 6. It's just where the numbers meet up. Does that make sense? It's like finding the common denominator in fractions. It's a similar mathematical concept. You're looking for the lowest common multiple. Let's try one more, because I'm going to leave these with you as practice, and then I'm going to show you where you can get infinitely more practice. Sodium and oxygen, sodium oxide. Sodium is what? Na. Oxygen is what? O. Sodium has how many electrons to lose? 1, so we'd say +1. Oxygen has how many to gain? 2. And again, usually I don't even write the second one yet. Usually I just, while talking about sodium, sodium gains 1 electron. So 1 sodium would gain 1. 2 of them would gain 2. 3 of them would gain 3. You could keep going. 4 of them would gain 4. 11 of them would gain 11. But we're good there. Oxygen wants to gain 2 electrons. So 1 of them, -2. 2 of them, -4. 3 of them, -6. I didn't actually have to go past -2 because that's where we get our balance. 2 sodiums can provide enough electrons for how many oxygens? That's right. So 2 sodiums charge balance with 1 oxygen. So how would we write that as a formula? Na2O. Good. Oh, Na2O. Yeah. Yes.
Does like half sprinkle matter in this?
No. The diatomic elements, or Hofbrinkel, if you like, has nothing to do with things when they're in compounds. It has to do with when they are alone by themselves. And that's not an ionic bond. All of the diatomic elements are making what kind of bond between each other? We learned about it yesterday. Covalent, right? Because obviously, by definition, diatomic elements are of equal electronegativity to each other, so one's not going to be able to take an electron from another. So you can't form an ionic bond between the same thing. It's got to be a covalent bond. Did that answer your question? Cool. By the way, I will leave the rest of these to you for practice. So I want you to practice these. This is your homework, is finish this page. But the naming is completely trivial. What would the name of this be? Rubidium fluoride, right? And obviously the name for this would be dirubidium sulfide. I'm pretty sure it would, because there's two of them and I'm the teacher. I'm the teacher, I have a degree in chemistry. It's not actually true. I have a degree in biology, despite having actually studied biochemistry, because I screwed up the paperwork when I applied to graduate. We don't talk about that. The point being, degree in biochemistry team, pretty sure it's dirubidium, because there's two of them. That's right. Because what kind of compound is this? Big dumb rock, all right? Do we use prefixes when naming big dumb rocks? No. We do not, so just be rubidium sulfide. What would the name of this one be? Are you packing up? There's like 4 minutes to go. I'll throw my pencil at you. That's what I'll do. Yeah, right at you. Right at you. Do you want me to throw it right at you? I will. I'll throw my glasses at you. Don't care. Don't care. That's how angry I am. And I got keys in both pockets. Wham! Just launch them. I will take you guys out. What's SRS? What's formula? What's the name? Strontium sulfide. Good. Not strontium monosulfide? Why not? Big dumb rocks. Now I want you to know something. If at any point you name an ionic compound with prefixes or a covalent compound without prefixes in this course, I will cry. Real tears. You'll get your paper back and you'll be like, what's this odd like watermark on the page? And then you'll know, oh, it's Orlando's tears. I made him cry. All right? I will cry. I will weep openly. Because that's a distinction we have to know. And again, I don't want you to know it as a rule. Don't understand it as like, oh, the rule says we name ionic compounds without prefixes and we name covalent compounds without them. Because that's easy to get backwards, right? It's easy to screw up. But if you understand why do covalent compounds get named with prefixes? Nice and loud.
There's many ways.
Because there's many ways you can put them together. So the name has to tell you how they're put together. Why don't ionic compounds need prefixes? There's only one way to put them together, so we don't need the name to tell us. Don't memorize the rule, understand the principle. If you understand the principle, you won't forget which way to do which one. You'll forget once in a while. I probably forget once in a while. People make mistakes, but you won't generally speaking forget. You know what I mean? You'll make little slip-ups, I'll cry, but you'll understand the principle. But if you try to remember it as a rule, ionic compounds, no prefixes. Covalent compounds, prefixes. Boy, that just goes right away, right? Like it's just so easy to forget. Yeah. 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 I probably ought not have given you bismuth yet, just because I don't think it's on our list from the previous page, did I? Okay, so for now, just skip bismuth. We'll get there, but I just don't want you going there yet. Where was that one? Was that in the homework questions? Look at me getting ahead of myself. Yeah, guys, cross this one out. I mean, you could figure it out, but just long story short, again, the middle of the periodic table, we have to look up what charges they take, and I didn't want you to have to do that yet, so I shouldn't have given you that question yet. So skip it for now. Sorry about that. Not a big deal. You can find a periodic table and look up what charge it takes, but again, I don't want you to do that yet.
I have a question for you.
Oh, okay. Maybe I have an answer for you. Maybe I don't.
So after high school, I want to become a chemical engineer.
Love it.
So I'm taking chemistry in next year.
So what I'm hearing is you hate free time. You hate having a social life. Message received.
Who needs social life? But would you recommend I take biology next year?
Here's the deal. Like, it can't hurt.